You have watched this happen. You ask a question, and the answer comes back one word at a time. Not all at once, at a pace steady and even, like someone typing on the other side. That pace is not the machine thinking, it is a physical limit, and it is not the one most people will point you at. Something in the hardware can only go so fast, so the words come out at exactly that speed, which raises a fair question. Because AI is supposed to be running on the fastest consumer hardware we know how to make. It runs on a GPU, a graphic processor, the chip that exists because somebody wanted to draw video games and which now does almost all of the artificial intelligence on earth. So why that chip? And if it is so good, why is your answer still arriving one word at a time? Here is the answer, and I'm giving it to you now rather than at the end. A GPU is good at AI because AI is one tiny piece of arithmetic repeated an absurd number of times. And a GPU is a machine built to do one tiny piece of arithmetic an absurd number of times. That is the whole thing, and everything after this is only about why it is true and what it ends up costing you. Your CPU is the main processor, the one that runs everything else on the machine. Inside it are cores, which are the parts that actually do the work, and a CPU has a handful of them. Each core is clever, each can handle complicated work with a lot of decisions in it, and each one works through its jobs in order. A GPU made the opposite trade, thousands of small cores, not one of them clever, all of them capable of doing the same simple thing at the same moment. And the arithmetic inside an AI model, which we are about to open up, really is that simple. Multiply a number, add it to another number, do it again. Not clever, just enormous. Draw a game and you are coloring 2 million pixels with the same handful of instructions, and run a model and you are multiplying billions of numbers with those same handful of instructions. To the chip, those are the same job. That is the answer everyone gives, and it is correct. It is also the half that does not explain what you watched at the start of this video. So let us do one word. Not in theory, one actual word coming out of an actual model. A model is a file, and inside that file is a very long list of numbers. And those numbers have a name. They are called weights. That is generally all a model is. Billions of plain numbers sitting in a file, each one a setting that got nudged into position while the model was being trained. There is no text in there, no sentences, no facts you could go and look up, just the numbers. To make one word, the machine takes everything you have written so far and multiplies it against those numbers, one after another, all the way through the file. Not some of them, all of them, every number in the file for every single word that comes out. Which means before it can hand you one word, it has to read the entire model out of memory. Then for the next word, it reads the entire model again. And again, every word of the answer, the whole thing start to finish. Now, those thousands of cores can do the multiplying almost instantly. That was never in doubt, and the real question was always how fast the numbers could get across to them. That speed has a name, and it is the most important thing in this video. It is called memory bandwidth, and it means how many gigabytes per second the chip can pull out of memory and deliver it into the cores. Think of it as the width of a pipe, and that width is fixed, a property of the hardware you bought that no amount of processing power will ever widen. Here is the shape of the problem. A byte is the basic unit of computer storage, about the size of one letter of text, and for each byte that comes down that pipe, the cores do roughly one piece of arithmetic. There is a name for that ratio as well, arithmetic intensity, and it means how much maths you get out of each byte you fetch, where about 1 is a terrible number to be sitting at. The cores finish and then they sit still, most of the chip doing nothing at all because the numbers have not got there yet. The cores were never the bottleneck, the pipe is. So the speed you can get is not a mystery. You can work it out on the back of an envelope. Take the bandwidth and divide it by the size of the model, and that is your ceiling in words per second. A model that takes up 4 gigabytes on a laptop class chip carrying something like 70 gigabytes a second gives you about 17 words a second. Put the identical model on a large data center card where the pipe carries thousands of gigabytes a second instead of tens, and the same sum gives you hundreds of words a second faster than you could follow. Same model, same arithmetic, the same multiplications in the same order to the same answer. The only thing that changed is how quickly the numbers could travel. Now that sum gives you a ceiling and nobody ever quite reaches a ceiling. Published results land somewhere around 60 to 85% of it because the software doing the work has costs of its own, and because reading the model is not quite the only thing going on. So the number is not a promise, it is a wall you cannot get past, and most machines end up somewhere just underneath it. One aside, because you will hit it the moment you go and measure this yourself. The machine does not count in words, it counts in tokens, which are chunks of text a little shorter than a word on average. And every tool you run is going to report its speed to you in tokens per second. The arithmetic is identical. When I say words and your screen says tokens, we mean the same thing. This explains two things you have very likely noticed and never had a reason for. The first one is that a bigger model is slower, and it is slower almost exactly in proportion. Twice the size, roughly half the speed. That looks odd if you imagine the machine thinking harder about a harder problem. And it is completely obvious the second you know it has to drag twice as much down the very same pipe. The second one is stranger. You can shrink a model and it gets faster while doing the identical arithmetic. There is a technique called quantization, and all it does is store each of those weights with less precision. So instead of a number recorded to a long string of decimal places, you keep a rougher version of it. The list is the same length, the multiplication are the same multiplications, the file is simply smaller. And it runs faster roughly in proportion to how much smaller it got. Nothing about the thinking changed, there was just less to carry. Now I have been unfair to those thousands of cores, and it is worth putting right. Reading your question and writing the answer are two completely different jobs, and they have names. The first one is called prefill. When you send a long prompt, the machine can work on all of it at the same time. Every word of your input in parallel across those thousands of cores at once. That part generally is heavy arithmetic, and it is precisely what a GPU was built for. It flies. Writing the answer is decode and it goes one word, then the next. Each one needing the whole model brought across again, and each one held up by the pipe. Same chip, same model, one job lights up the entire processor. The other leaves most of it sitting in the dark. That is why a very long question costs you surprisingly little, and a very long answer costs you a lot. I have explained all of this with one pipe and a wall, of course, and I should say plainly that the picture is simplified. There is a great deal of cleverness inside a real chip that I have skipped straight past. But there is one complication worth having because it explains something you have felt. Everything so far assumes the machine is answering you and only you. One person, one conversation. The whole model dragged across for every word you get back. Now put 1,000 people on that machine at the same moment. The instant those numbers arrive, they can be used for all 1,000 conversations at once. One trip down the pipe, 1,000 times the work out of it. And that ratio, the one that was stuck at about one operation per byte, climbs hard, and if you push it far enough, the course become the limit again, which is exactly where a GPU wants to be. That is called batching, and it is the reason a hosted model can feel quicker than the exact same model running on your own machine. Your machine has one conversation to work with, theirs has thousands. Three sentences, and then I'll let you go. To write one word, the machine reads every number in the model. The pipe carrying those numbers is narrower than the cores are fast. So the size of the model and the width of the pipe set your speed, and raw processing power mostly does not. So are GPUs good at AI? Yes. Thousands of small cores, one tiny piece of arithmetic repeated forever. That is a real answer, and it is why they got the job. They are just not as good as you would expect, and now you know what to blame. One thing I would like from you, and it costs about a minute, look up the memory bandwidth of whatever you run models on, divided by the size of the model file in gigabytes, that is your ceiling. Then run the thing, see what you exactly get, and put both numbers in the comment. I want to know where real machines actually fall. The published figures cluster somewhere between 60 and 85% of that ceiling, and I would like to see whether the machines people have at home land in the same place. All right, if you like the video, make sure you like and subscribe. Thank you for watching.